We're going to finish our notes on our assignment 12.4 page. We've already learned that a rational function is the ratio of two polynomials. It must have variables in the denominator. Fractions aren't enough. It has to have variables in the denominator. We know that a fraction is equal to 0 when the numerator is 0. We know that we can never have 0 in the denominator, so those will be our undefined values, and they'll look like vertical asymptotes on our graph. Okay, so let's try another one of these. And 5a, this graph will give us some complicated ideas about rational functions, and then we'll keep practicing until we see lots of different examples. Okay, find the intercepts, find the asymptotes. To find the intercepts, if I put 0 on the y side, that's g of x would be the y coordinate. When is a fraction equal to 0? When its numerator is 0. So x equals -3 would make the numerator equal to 0. And how do we find the y-intercepts? We put x equals 0. If x becomes 0, all that's left here is 3 divided by -4. So our y-intercept is at -3/4. The vertical asymptotes are the values that make the denominator equal to 0. So at -2, and please label the equations of your asymptotes, and at +2. So those are the forbidden values, and we know that a rational function will never cross a vertical asymptote. The horizontal asymptote depends on whether the numerator is growing equally fast with the denominator. Here the denominator is a higher degree than the numerator. So the denominator is growing faster than the numerator. And I suggested that a way to remember this was that concept of if you only had a few pizzas but you were dividing them among many, many guys, that 3 over 1,000,000 would be the same as having no pizza whatsoever. So when the denominator grows faster than the numerator, then we get an asymptote at 0. So right on top of the x-axis, make it visible. So I'm going to put a dotted line here and label it y equals 0, so no one can miss the fact that that is a horizontal asymptote. Okay, right away we might have a question that occurs because we already put a point on that. Oops, didn't mean to erase that. We already had a point on that horizontal asymptote. Well, that's okay. A function can cross a horizontal asymptote, but it will never touch a vertical asymptote. Okay, how do we finish this graph? Well, there's where the hard work comes in. We simply have to try some values of x and see what we get for y. And again, I don't care about being extra precise here, just as long as I get the general shape. Okay, so as long as we were just talking about this intercept here at -3, let's see what happens if we pick some values that are negative. So for example, if I picked g of -4, let's see what's happening. The numerator would be -1, and the denominator would be 16 minus 4, or 12. So it looks like we're getting values that are very close to that horizontal asymptote, but they're actually negative. They're below that asymptote. And you could see what's going to happen if you wanted to continue by choosing numbers like g of -10 and find out what happens. On the other side, I can't pick -2. That's on a vertical asymptote. So I might say, well, the best I can do is to choose -2.5. And I'm going to write that as -5/2. And you could grab your calculator if you don't want to do this arithmetic. But if I put -2.5 into the numerator, I will still have +1/2. And if I square this, I will get 25/4 minus 16/4. So I will have 9/4 in the denominator. And we know how to divide fractions. We multiply by the reciprocal, and we will come up with 2/9. Now, again, you can use your calculator. You don't have to worry about all of this arithmetic. But when we were at -5/2, our y-coordinate is +2/9. So I'm going to tell you that this is enough for me to know that once it's headed up, it's going to continue going up to infinity. And on the other side, what did I do? I just stayed close to the horizontal asymptote. All right, what do we do between these two graphs? Well, I already have this y-intercept, but I don't know the shape in the center of the graph unless I try some more points. So let's find out what happens at g of -1. I put it into the function. I get a numerator of 2 and a denominator of -3. So -2/3. And I made that look a little horizontal, but you got the idea. And at +1, let's see what happens. If I put 1 in for x, we get a numerator of 4 and a denominator of -3. So we're a little bit lower. So I don't really know the shape of this, but it's enough to convince me that it's decreasing here. Okay, you might need to try some more points. You might say, I don't see that so obvious. Maybe you would want to say, I want to find out what happens at -1.5. So you can graph some additional points once you get the idea of the basic shape here. Okay, and then what's left? Well, we've got this region over here where x is bigger than 2. So let's find out what happens if we choose 3, for example. So if I put 3 in for x, our numerator is 6 and our denominator is 9 minus 4 or 5. So I get 1 1/5. So it is a little higher than that maybe, but it's above this, and I'm going to go up to infinity again on that side, and I'm going to approach the asymptote. Now, how do I know it stays above the asymptote this time? Well, I kind of was thinking ahead about the arithmetic. If you say, I'm not so sure, then try it. Let's put 10 in there and see what happens. We would get 7 over 96. So I kind of could see that the numerator was positive and the denominator was going to be very large. So remember that when the denominator gets large, the value of the fraction gets very small. So that's how I knew it was going to be positive on that side. Okay, so this is a fairly complicated graph to describe with limit notation. So let's see what happened here. What happened as x, that's horizontally, as x gets closer to positive infinity? As x goes to positive infinity, I'm looking at this section of the graph that I just circled. As I choose bigger and bigger values of x, the y-coordinate is going to 0. On the left-hand side, what happens as I choose smaller values of x? Well, it was also getting close to 0. The difference here is that it was getting to 0 from the positive side here and from the negative side there. A little bit bigger than 0 on the right side, a little bit smaller than 0 on the left side. The next question says, what happened as x approaches 2 from the positive side? That means from the right side. What happened as x approached 2 from the positive side? So we're looking right here in our graph. As x is getting closer to 2, but we're marching in from the right side. And there the graph was going up to infinity. And our other question here says, what about 2 from the small side? So now what happens if we're approaching 2 from the left side instead? Well, there's nothing up there. I've got to switch down here. Here's where the action is on the small side of 2. On the small side of 2, the y-coordinates are going down to negative infinity. So each of these questions is asking you to zero in on a piece of the graph. What happens as x approaches -2 from the positive? That means the right side. What happens in our graph as we get close to -2 from the right-hand side? Our graph is going down to negative infinity. And last, what happens as our graph is approaching -2 from the small side? This means from the left side. So find a place on your graph where the x-coordinates are getting closer and closer to -2, but they're smaller than -2. So that would be this section right here. And our y-coordinates are going to infinity. Remember that g of x is just another name for the y-coordinate. All right, I think I have GeoGebra running. Let's see if we can take a look at this graph quickly and see if we like our shape, and I think it looks pretty good. We can see here that the graph was a little bit below the horizontal asymptote. Let's see if I can get a asymptote to show up there on the axis, and our vertical asymptotes, if GeoGebra will let me select them, and -2 doesn't quite like the stylus while the video is running. There we go. There's our 2 vertical asymptotes. So our graph was very accurate, even though it didn't take us too long to make it. Okay, let's go back to a summary. Remember that you have all of this information summarized on the second page of your handout, but here's what we're going to do. To find the y-intercepts, we set x to 0. We set the numerator to 0 to find the x-intercepts, the denominator to 0 to find vertical asymptotes. The horizontal asymptotes depended on the degree, that's the power, of the numerator and the denominator. So when the denominator had a larger degree, so for example, if we had 5 over x minus 3, the denominator grows larger. If we had another example where we had x squared in the numerator, but x cubed in the denominator has a higher power. So for these types of examples, the x-axis would be your horizontal asymptote. We just saw that in our previous example. What if the degrees are equal? Well, then we're going to use the ratio of the leading coefficients. So let me show you a quick example. We did one in class that was like this. What if the numerator is growing at the same power as the denominator? Well, if these are both x squareds, as x gets larger, they grow at about the same rate. The -1 and the 3 will become negligible when x is very large. But what we know is, if you think about this numerator becoming close to 2 billion, the denominator would be close to 5 billion. So when the degrees are equal, we take the ratio of the leading coefficients as our horizontal asymptote. And you're going to practice this some more. It'll be very clear if we take a few days for this. Here's another example. If we had 3x over x plus 2, the ratio of the leading coefficients, because these are both first powers, so our horizontal asymptote would be at y equals 3 over 1. What we won't cover yet is what happens if the degree of the numerator is larger than the degree of the denominator. Then we're going to do long division, and that's a process that we have yet to talk about. So we'll practice some of these basic ideas first.